The biggest shift this week is that generative models are starting to beat the trade-off between quality and speed without leaning on brittle, frozen tokenizers, or slow sequential decoding. In images, pixels, and even 3D meshes, the same pattern is emerging. Keep more of the structure continuous, train the model closer to inference, and let it learn representations that are actually easier to predict. That means sharper samples, less error accumulation, and much faster generation. The interesting part is how these systems get there and why one of the most common design choices in modern generative AI may be about to look outdated. Let's explore the first paper. Gear-guided end-to-end, autoregression for image synthesis. Gear, or guided end-to-end autoregression, from Peking University and Tencent Hunyuan, reframes visual generation by training a vector-quantized tokenizer and an autoregressive generator together instead of freezing the tokenizer first. Its core technical move is a dual readout of the discrete codebook assignment. A hard one-hot branch trains next token prediction on the exact inference tokens, while a differentiable soft branch carries a representation alignment loss back into the tokenizer, avoiding the collapse seen with straight-through estimation. On ImageNet, 1K at 256 times 256, Gear improves over LlamaGen Repa at every scale. With classifier-free guidance, GFID drops from 6 to 4.95 for the 111M model, from 3.15 to 2.95 for 343M, and from 2.68 to 2.52 for 775M, while reaching up to 10 times faster GFID convergence. The same tokenizer transfer works on text-to-image synthesis with GPICs 100M, image corpus, and Qin3 17B conditioning, where Gear lowers FDD to 256.9, 177.4, 138.0, and 115.3 at 50K, 100K, 200K, and 390K steps, respectively. Ablations show the method is quantizer agnostic across VQV, LFQ, and IBQ, and that replacing the soft bridge with STE catastrophically degrades generation to GFID 104.932 and RFID 59.723. Representation analysis finds an important reversal of diffusion style alignment. The tokenizer becomes less DNOF2, but the AR hidden states become more patchwise DNOF2, and more spatially coherent, which explains the improved predictability and sample quality. Let's explore the second paper, Parallel Rollout Approximation for Pixel Space Autoregressive Image Generation. Parallel Rollout Approximation, developed by Jiayi Xu, Di He at Peking University, and Guolin K at DP Technology, targets a hard problem in pixel space autoregressive image generation. Directly predicting 16 times 16 times 3 pixel patches causes large single-step errors, while teacher-forced training creates train-inference mismatch and error accumulation. The method keeps a pixel-in, pixel-out autoregressive interface, but internally predicts compact 16-dimensional intermediate states, then decodes them back to pixels with a learned causal pixel decoder. It also approximates inference time rollout during training by constructing decoded, inference-like pixel inputs in parallel through the same state-to-pixel path used at test time instead of expensive sequential on-policy sampling. On class conditional ImageNet, 1K at 256 times 256 resolution, PRAS with 135M parameters reaches FID 2.58, beating the previous billion-scale pixel space autoregressive result of 3.6, while PRAL at 511M parameters improves to FID 1.94, a new state-of-the-art for pixel space AR models. Diagnostics show that using low-dimensional intermediate states and decoded pixel inputs is complementary. For 256 times 256 generation, direct high-dimensional AR drops to FID 7.68. Input noise injection alone only reduces 9.94 to 7.68, and the PRA decoded input path yields 2.88 in the ablation setting. Beyond generation, PRAL also reaches 68.8% top 1 accuracy on ImageNet linear probing, outperforming both diffusion and latent space AR baselines and indicating that end-to-end pixel space autoregression can support stronger visual representations. Let's explore the third paper, Polyflow Continuous Topology, Embedding Flow, Matching for Artist Style Mesh Generation. Polyflow from Tencent Hunyuan reframes artist style mesh generation as continuous flow matching by introducing a compact topology embedder that converts discrete mesh adjacency into a continuous per-vertex embedding recoverable through space-time distance thresholding. Instead of auto-regressively decoding tokens, the model denoises a unified vertex state XYZ, normals, topo in parallel with a flux-based DIT transformer conditioned on frozen point cloud features from Hunyuan, 3D, Omni, then reconstructs edges and faces exactly from the generated embeddings. This design removes sequential error accumulation, gives exact user control over output vertex count, and generates meshes in seconds rather than tens of seconds or minutes. On Toys 4K, Polyflow achieves the best fidelity among BPT, Mesh Anything v2, Deep Mesh, and Fast Mesh, reaching 0.008 chamfer distance and 0.021 Hausdorff distance, which the paper reports as 43% and 40% better than the strongest autoregressive baseline, BPT. The topology embedder is most effective at 32 dimensions, where edge reconstruction reaches 0.9991 f1 and inference scales to 4,000 vertices in 5.88 seconds on a single NVIDIA A100, compared with 36.72 seconds for Fast Mesh and 554.5 seconds for BPT. That's a wrap on today's AI paper highlights. Thanks for watching.